Hi everyone. I've been doing the feedback on problem set 6, and I'm writing a lot of the same comments on a lot of people's submissions, and so I want to just put this all in one video and kind of point everybody to this instead. So I want to do a couple of examples of these types of questions that we saw in problem set 6, just to kind of talk through the strategy and think about what are the reactions that we're using to make this happen. So the first example is here. We start with a 1,3-dicarbonyl and we go to this acid chloride as our final product. And so whenever we see a 1,3-dicarbonyl, we should immediately start to think about um, two things. One is reaction at the alpha position. Right? And the alpha position is, of course, this one here. And then the second thing is we should think about decarboxylation. And decarboxylation is usually a two-step process. Step one, we convert the esters to the carboxylic acids. So you can do that either with acid or base. I'll probably just use sodium hydroxide here, but you could also use H plus H2O. And then the second step is heat. So we're going to use both of these to kind of get from starting material to product, but there's other things that we also have to consider as we do this. So the first thing to consider is, where is this alpha? So if the reaction is going to occur at this alpha position, where is that alpha position in our final product? Right? In this case, the alpha position is still going to be an alpha position. So this circled carbon here is going to correspond to this alpha position here. And so what we want to look at is what is added. So question one is kind of what is added to the alpha position. Right? So we have a carbonyl on one side, but there's already carbonyls over here. So using what we know from previous in the course, right, we can convert carbonyls between lots of different things. If we need to convert an ester to an acid chloride, that's something that we know how to do. Right? What we can't do is, what we only have kind of one strategy for is adding things to the alpha position. And so in this case, what we're going to add to that alpha position is we're going to add all the rest of this stuff, right? So everything to the left of this alpha position, these 8 carbons, if I can, are the thing, that's the answer to this question. What's added to the alpha position? 8 carbons are added to the alpha position. And so that should be kind of the first thing that we tackle before we do decarboxylation, before we worry about this acid chloride, because this is a 1,3-dicarbonyl, that makes this alpha position particularly reactive. And so the first thing we're going to do is we're going to take advantage of that reactivity and make the reaction happen at that alpha position. So the first thing I'm going to do is I'm going to take a base, make the enolate at that alpha position. Step 1, OCH3. That's going to make the base, or that's going to make the enolate, excuse me, at that position. So we get the removal of the hydrogen from the alpha position, we make the enolate, and now I'm going to add those 8 carbons. Now, what way are we going to add those 8 carbons? We have a lot of different reactions that can occur with enolates. I want to quickly jump to a future slide here. Oh, I missed it. There it is, right? We have basically 4 different possible things that we can do with enolates. 5 if you count bromination. We'll get to bromination here in just a minute. But the 4 things we can do an SN2 reaction, we can do an aldol reaction, we can do a Claisen reaction, or we can do a Michael reaction. And the way that we pick between these reactions is we look at what does the product look like, right? If we have a product that has carbons added to the alpha position and have no other functional groups, no other oxygens or anything, right? The answer there is going to be, we're going to react with an alkyl halide, because the enolate will add to the alkyl halide, we'll lose the leaving group, and we'll add only the carbons. So in this case, we have 7 carbons. Those 7 carbons get added to the alpha position. If we have an alcohol in our product, that's going to favor the aldol reaction. If we have a ketone in our product and it's a 1,3-dicarbonyl, we're going to favor the Claisen reaction, or we're going to choose the Claisen reaction. If we have a ketone that's a 1,5-dicarbonyl, we're going to use the Michael addition. right? So knowing what our product looks like gives us a ton of information about what type of reaction we're going to choose and also what reactants we're going to use to make that work. Okay, so in this case, we're adding 8 carbons, and notice there are no functional groups, right? No other oxygens are added to this molecule. So that means that we're going to use an SN2 reaction, which means we just need a leaving group attached to the correct carbon. So this is my 8 carbon fragment. I've added a bromine to kind of the 8th carbon here. And so when this enolate comes in and reacts there, kicks out the enolate, or kicks out the leaving group, we're going to get our 8 carbons now added to our structure. And now once we do that, now we can start to worry about the other stuff. Now we have enough, we have all the carbons that we expect to have in our final product are already attached to our structure. So now all we need to do is we have 2 things we need to do. One, we need to get rid of one of these carbonyls because there's only one carbonyl in the product and 2 here. And 2, we need to convert these carbonyls to the acid chloride. Right? So this is where decarboxylation comes in. Sodium hydroxide is step 1. Step 2 is going to be heat. And I'm going to lose CO2. So I lose this whole group over here, right? I convert both of them to carboxylic acids and I lose that group. You'll recognize this reaction from problem set 5. We had a question almost exactly like this here. Right? And that gets me here. Now this is very close to our final product, right? Well, the only difference, we have the right number of carbons and everything. The only difference is we have a carboxylic acid and we need an acid chloride. And so now we just have to reach back in our memory banks and think, how do we convert acid chlorides to, my numbering is all off, 3, 4, and 5, right? Acid chloride to, or carboxylic acid to acid chloride is thionyl chloride. And let's see, that's alpha carbon 1, 2, and 6. That's our final product. Right? So the strategy here is to start at the alpha carbon, add the things that are needed for the alpha carbon, and then worry about the carbonyl reactions, right? Here, we need to convert these to carboxylic acids to do decarboxylation. So we add sodium hydroxide to do that. That replaces each OCH3 with OH. We lose CO2 with the heat here, and then we convert this to thionyl chloride. So when you look at the questions in problem set 6, these are the processes that I'm hoping that you'll think. Every question in problem set 6 starts with a 1,3-dicarbonyl. And so we should always be thinking about reacting the alpha position and then thinking about if we do decarboxylation, how does that get us toward our final product? All right, one more quick kind of similar setup here, but we can go through this pretty quickly. Once again, we start with a 1,3-dicarbonyl. And so once again, we're going to be reacting at the alpha carbon first. So let's find that alpha carbon in our final product. Hopefully it's clear that that's the alpha carbon, right? Our R group, whatever that R group is here, carbonyl, and then the alpha position. Now, notice in this case, what are we adding to the alpha position that wasn't there before? Now we have 2 different groups, right? So this time we have 2 groups added to the alpha position. And we have 2 different types of groups, right? Up here, we have 3 carbons with no functional groups. No functional groups. And so immediately our mind goes to the SN2 reaction, right? Which we used in the previous slide. But if we look at the other group, notice that this other group is not connected to the first group that we circled, right? They're both connected to the alpha position, but they're not connected to each other. So we can't add these groups in one step. It's going to take 2 separate steps to add the 3 carbons that are up there. And then our second step is going to be, where's my marker? There we go. 7 carbons. And notice that this has an alcohol in it as well. Okay, so we go to our list of enolate reactions, enolate products, and we look at this and we say, okay, alcohol product, that is this one, right? It's a beta hydroxycarbonyl. That's an aldol reaction. So that means that we need to react or enolate with an aldehyde or a ketone. So we can do that. Now this is one where it doesn't matter which one you do first. You can either do the SN2 reaction or the aldol reaction. I'm going to do the aldol first. Notice that I have 7 carbons here, right? And I have an aldehyde, so I know that when I make my enolate, that enolate is going to add to the aldehyde, right? I guess I could draw that. When that adds to the aldehyde, right, we break that pi bond and we get this. So this was the mechanism, again, that was on problem set 5. So now we've added our 7 carbons. We have our hydroxy group here. With a little bit of workup, we could add H plus to that. But what we're going to do is now, for steps 3 and 4, is we're going to make the enolate again. Notice that there is another hydrogen here, so we can still remove another hydrogen from that position. And now we're going to do our SN2 reaction that removes, or that adds in these 3 carbons. And now we get to something that is even more of a mess, just because it's got a lot of stuff on it. So there's our 3 carbons. Here's our alcohol. And there's our 7 carbons. So we have our 3 carbons here. Whoops, I don't want to do that. We have our 3 carbons that we just added. We have our 7 carbons here. To get from here to the product, all we have to do is get rid of this carbonyl group. So once again, we're going to do that by decarboxylation. Sodium hydroxide converts the ester to the carboxylic acid, and then heat will lose CO2, and that goes away, and we're left with to our alpha carbon. Now we have 1, 2, 3 carbons there, and if we go down, we have 7 carbons there. Okay. So the strategy when you have multiple things added here is not to try and add everything at once, but instead to do kind of this iterations of the same process. Make the enolate, bring in whatever the needed electrophile is, right? So we make the enolate, we bring in our 7 carbons. We make the enolate, we bring in our 3 carbons here. The way that we know what reaction to do is we have this kind of list, if not a physical list, at least a list in our heads of what these products look like. When I have alcohols in my product, that means an aldol reaction. When I have a 1,3-dicarbonyl, that means I want to make a Claisen. If the question calls for a 1,5-dicarbonyl, then we need to do a Michael reaction, okay? So as you're thinking about these reactions, as you're thinking about problem set 6 and the revisions that I'm asking you to do, go through this strategy. Think about what the alpha position looks like. Think about what groups are being added to that alpha position. Is there one group? Are there 2 different groups, right, that are being added to that position? And then think about what the pattern of those groups tells you about the reaction that's taking place. So this is my best advice for how to tackle the revisions to problem set 6. If you got a link to this video in your feedback, that means that these are the types of questions that we're giving you issue, and I want you to use this strategy to kind of make sense of these questions. I hope this is helpful. If you have additional questions, please don't hesitate to email me. Thank you so much. I will talk to you soon.